today we're going to do section 8.3. So first let's scan the book. All right. Let's see. That is okay. That's the whole page. And then let's get a little closer on top. Okay. And closer on the bottom. Let's see. Did I? That should be it. Next, page 270 and 271. That's the homework page, basically. It's a short section, somewhat short. Yeah, something like, maybe like that. All right. And then a little closer on top. And a little closer on the bottom. Let's see, is that close enough? Maybe the top wasn't close enough. All right, that should do it. So let's begin on page 268. That is the 8.3. Other indeterminate forms. That's talking about such as subsection 3.1. There's the form 0 times infinity. Of course, we're familiar with. And next page, there's the form infinity minus infinity, which would be hard to do. But we've done this before, right? And then later you see there's even other miscellaneous types such as 0 to power 0, 0 to the power infinity, and so on. And all these we have done in Calculus 1 or 2 or whenever this was taught. So please read this whole section yourself, okay? Starting from the beginning of page 268 all the way to the other side, because there's nothing here that wasn't mentioned before. Okay, all this is old news. There's nothing new here, and you notice there is no new theorem being proved. So you can totally read this yourself fairly easily, I think, and do all the examples. They are also fairly straightforward, and also the following page. This is page 270. Through all the examples, you notice how short they are. So please go over all of them yourself. Make sure that they all make sense. And as I have done, well, I don't know if I did all of it or some of it. Now let's see. Well, anyway, so that is I have started on example C. All right, and then of course the other examples E, F, G, H, I, yeah, and did all that. So please do this yourself. Let me see something here. So I don't think you will have much trouble doing it yourself, because I did this by hand and I didn't really write much more than what the book has. It looks all quite straightforward. I think example A and B are even shorter or something. But anyway, yeah, so please read all those pages by yourself, and then we'll come to the homework. For homework, please do problems on page 270. Where'd it go? Oh, yeah, right, on the next page. For homework, please do essentially do all the problems from 1 to 11, and then do problems 15 to 23. So, yeah. And at the homework problems, you might think, well, if the text problem is so easy, maybe we should just skip the homework too. But the homework problems are not easy, okay? At least not all of them. And some are somewhat short, whereas others, for example, I was completely stuck on problem 4 for the longest time until I finally figured out a trick to do it. And then, in fact, for problem 4, I even looked up on the internet to see how, Googled it to see how it's done. And the Google tells me to use Taylor expansion, which is okay, except that we haven't gone through that yet. That's in the next section. So I have to be able to do problem 4 without any future knowledge, right? We have to do it with what we know. And I did eventually manage it after several tries. And so that's problem 4. And then anyway, so these problems are quite a bit harder than what we used to do in basic calculus, and which is why they are worth doing. So please take your time and get all the homework done. And then when you're finished, I want to talk about them. So now that you are done with your homework, let's talk about it. First, problems 1, 2, and 3, I think they're quite straightforward, so I'm not going to go into details here. I did them all in one line or almost one line, and you just follow what the book says, right? And slap the E. This one, slap the E on there or something, and then once we figured out that this thing converges to 1, then minus 1, then don't forget to put the E back, okay? Otherwise, you're going to get the wrong answer, which I've done before. And so that's problems 1 to 3. That should be okay. Now, problem 4 is when I was stuck, okay? And first, I was trying something. As you notice, doesn't work. Forget it. I guess I scratched it all out. And then I tried again somewhere. No, not here. So then I did problem 5 and 6 instead, and did okay. So let me see, 5 and 6, okay. And then continuing, I think I had more trouble with problem 6, but not that much problem. Eventually, I got problem 6 done. So after I finished 5 and 6, then I decided to try problem 4 again. Still failed. I had a new idea, see, but the idea didn't work, so forget that. So then I forget that, and then so I did problem 7 instead, and then I tried problem 4 again, and it still failed. So then we'll go to the next. But I don't think I failed completely. I think at this point I figured out how it was done. Yeah. So it wasn't a failure, but it was a mess. So I decided to rewrite it. So eventually on the next page I was able to do problem 4, where we have the log of x and log of x. So then when you stick this thing on top, then with the E on it, then you have log of x, and the integration gets into such a weird mess that I didn't know what I was supposed to do. But by now, however, I figured out the trick. That is, I think I learned it from doing problems 5, 6, and 7, where it reminded me that we have a big complicated thing, but we can perhaps separate them into 2 chunks. And see if each chunk goes anywhere. So I separated it into, so this is the original chunk, right? I separated it into 2 chunks. The green part, is that green? It might be green. And the pink part. So then the pink part, it comes out much better, okay? After working with the pink part for a while, I figured out that it equals to 1. So that's the pink part. I don't know, 1 or minus 1. Why does it say minus 1 here? Let's see, which one equal to 1 and which one equal to minus 1? Let me read it. It's hard for me to read it on the computer screen. Oh, I got it. The pink part eventually becomes minus 1, and that's not as hard to do because you have less stuff. Okay, this stuff can come out pretty good. And then the green part then becomes equals to 0. So eventually the answer, you put the E back, is minus 1 times the 0, which is e to the power minus 1 times 0 is just positive 1, which is the answer at the back of the book as well. So the reason I was able to do problem 4 was because I did problem 5, 6, and 7, and those problems gave me ideas of how to go about problem 4. So that might be a trick that you want to do, that if you see a problem that's tough to do, and after you struggle with it for a while, you might want to do a different problem, and that might clue you in or open your mind or something, or something. Okay, so that is what I did. Now, so next, let's look at the next problem here. Okay, so next, let's look at problem 5. We have the limit here. Problem 5 wasn't so simple, although it wasn't terrible, I guess, because I was able to do it in one try. So what happens is that we confirm that it is a 0 over 0 and then infinity, I guess. Which we slap the E on there, okay, that gives us, and confirm that tangent x over x is equal to 1, so then so being that the tangent x over x is 1, then we have a log in there, so log of 1 is going to 0, so we confirm that this is an infinity times 0 situation. And so we can and so we force the x, well, we'll rewrite the x on the bottom, okay, and then it becomes a 0 over 0 situation. and then we'll take the derivative of top and bottom we got here. I used the calculator. I wasn't going to take that derivative by hand. Anyway, so I used the calculator and I got this, which is still a 0 over 0 situation. I took the derivative again. I got here. And at this point, what I did is, let's see, well, might even be able to do this sooner. I don't know. Okay, but anyway, this is what I did. At this point, I used the trick of dividing everything by tangent x. That way, and the x's cancels out. So then we have just secant squared x on top. And remember, secant x as x approaches 0 is 1. Okay, so we have reduced the numerator into 1, and then the denominator becomes 2 plus x secant squared over tangent. And what is that? So I calculate that separately here. The purple part, see? The purple part, that part calculated to be that equals to that, which goes to 1. Because x over sine x does equal to 1 as x approaches 0. And cosine x is just 1, so the whole thing goes to 1. So this thing, the answer then, so this part then becomes, this thing goes to 1, so the whole thing then becomes 1 over 2 plus 1 is 1/3. So the answer is e to the power 1/3, and that checks out. Why, that is the same as the answer at the back of the book. So that is that. I also happen to have plotted this thing in Desmos to as a further confirmation that this is correct. Okay, and you can do this with any of these limit problems. Just plot it and see where it goes. You know, and we don't need any rules to see the answer. See, the green line is the problem, and the purple line is e equals to the 1/3. And you notice that at 0, they are on the same spot. So it must go to e to the power 1/3 at 0. So that is a further confirmation that this is correct. So that's problem 5. And then problem 6, I had some trouble with. Let's see, which way am I flipping the page? Over here. Okay, so problem 6, I tried something and didn't quite work. So I Googled it online, and the Google shows me a very neat trick. Okay, and that is how we can do this. So we do this thing, right? And then we end up with some kind of a thing here. And so now what? And the Google says we're going to multiply it by this fraction. Why? Because x over sine x equal to 1, right? As x goes to 0. So we're just multiplying by 1. So we're good. So once you multiply this by this, so this, in other words, this thing got turned into this thing, but the purpose is to get rid of the sine squared x on the bottom. Okay, so that we have only x to the power 4 left. So this arrangement, this arrangement increased the power on the x bottom to be 4, but it got rid of sine x, which is a big improvement, because x to the power 4, if you keep taking derivatives, is going to disappear, whereas sine and cosine doesn't. Okay, they'll just keep churning themselves, and then there's no end to sine and cosine if you keep taking derivatives. So that's a very neat trick, right? So x over sine x, it got rid of the x to the power 4, so we only have to take the derivative, to calculate the limit of this thing, because this, and beginning that's 1. So doing that, so now we have the x to the power 4, so I took the derivative 4 times. So the bottom then becomes 4 factorial. The top, each time you take derivative, the top is 0 until the last time. Okay, so you have to confirm that, because the L'Hopital's rule requires that the value is a 0 over 0 format before you can take the next derivative. So I took 4 derivatives, and I made sure that everyone does go to 0 before I take the next one. And using the calculator, of course. I wasn't going to do this. But anyway, and so the 4th derivative came out to be this big long thing. And it's not even that bad. It could have been worse. So anyway, at this point, the bottom is no longer 0. So the top had better become something. And the top turns out to be 16. Yeah, that's because x goes to 0. So this is gone, that's gone, and that becomes 16. So 16 over 24, or 2/3, and that is the right answer. The book did not give an answer to problem 6, but of course, we are fully able to use Desmos, right? So I plotted the original function in Desmos, and also the line 2/3. And notice at 0, they do come together, right? It does equal to 2/3 as x approaches 0. So that's problem 6. Very nice to have Desmos around, right? How would I have done this without it? I don't know. But anyway, so there's that. And then problem 7, did I have 7? Yes. Okay, problem 7 is, here it is, problem 7. We're supposed to do this thing. All right, so in problem 7, we're going to pull the same trick where we have a 0 times infinity situation here. So we make something go to the bottom, the sign becomes cosecant or something, and then take the derivative, which landed us with this stuff right here. Okay, and then we notice that there's out of this mess we got cosecant turns into sine on top, and we have sine x minus 1 over x, which goes to what? Now give me a second here. Okay. And the reason I look confused is because I thought x was going to 0. No, x is going to 1. All right. So then this just goes to 0. Okay. So the question is, what does this chunk look like? So let's calculate this chunk, which turns out to be a 0 over 0 situation. So we can do the L'Hopital's rule on it. Okay, and see if it ends up being infinity or something, then we're stuck. But if it doesn't end up being infinity, then we might be able to come to the right answer. And so this is the second chunk over here is when we apply the L'Hopital's rule, it equals to this thing, which goes to 1. Okay, because secant of 0 is 1, and then x is going to 1, not 0. So this thing just goes to 1. So the original answer, put the e back, is 1 times 0, which is equal to 1. Okay, e to the power 0 is 1. So that is the answer to problem 7. Let's see here. Okay, and so that's that. Yeah, the 1 is the right answer by the back of the book. So I didn't plot it as a result. Okay, so next let's look at problem 8. I think 8, 9, 10, and 11 are all quite straightforward, and then don't think there's much worth mentioning. But I have written down here. They are each one-liners, and they should be okay. So 8, 9, and then 10. What happened to 10? Let's see. I will. No, I'm not so sure. Okay, 11. 11 is for sure. I mean, infinity to infinity is definitely infinity, right? Oh yeah, what I should say is 10. 10 looks weird at first, but it's infinity times minus infinity. That's just negative infinity to extra negative infinity, extremely infinite. Negative infinity, so e to the minus infinity is 0. So that's 8, 9, 10, and 11. I have plotted the 8 problems, 8 and 9 here. Which to confirm, because I don't think they had their answers at the back of the book, but problem 8, as you can see, as x goes to 1 from the positive side, it does go to infinity. Here's the graph. And then oops, I'm moving it the wrong way. Okay, problem 9, same thing. Okay, as the function goes to, what is this, 1 from the left side, you can see that it does approach 0. That is on the ground. So that is how we can check our answers to make sure that it is indeed correct. Okay. So problem 10 and 11, I also plotted it because I think there's no answer at the back or something like that. As you can see, when x goes to, where's x going? This is pi over 2, right? If it goes on problem 10, I think it was, one of them is pi over 2 goes from the positive side, and then as you can see, it approaches 0. But on the negative side, then it approaches infinity. So that is, and the graph looks very nice, okay? I only showed part of it here, but the graph just continues to do that funny wiggling and looks very cute. So that is problem 10 and 11. Next, let's look at problem 15, which is problem 15 is a bunch of algebra, okay? Try to do the algebra correctly. Well, I messed up the first time I tried, and I had to do it again. And what's the funny thing is, I messed up and still got the right answer. But then I got to thinking, what did I do? It was a complete disaster. So I had to redo it. So here's the redone. And that's the one thing about this kind of stuff. Because things go to zero a lot, sometimes you can do the wrong thing and still get the right answer. But anyway, so once you do the right thing, okay, the standard trick of a radical is you do the +1, and then factor out some of the stuff, and gives you something, and it all comes out very nicely. So that's problem 15. And problem 15, I think there is not the answer at the back of the page, so back of the book, so I made sure that this is correct. Okay, and of course we have our trusted Desmos, and look at how beautiful the graph is. It looks awesome. And then so you notice it approaches y equal to 5/4 very, very quickly. Look at how fast it got there. But anyway, yeah, so that's that. And it looks very, very nice. Okay, it's perfectly smooth and everything. So that's problem 15. Next, we are going to do problem 16. 16 is the same deal, except that it's a cubic root. And we don't do cubic roots that much, right? And so to do the cubic root, you have to remember how to this good old this thing is now to do this. The square root, we had to use the difference of squares principle. So to use the cubic root, we use the same principle, okay? And use the difference of cubes formula, which is right here. And from algebra, right? So then so following this formula, we write this stuff out. What is that? Yeah, we multiply top and bottom by those things. And in other words, we need to multiply top and bottom by this thing right here. Okay, with proper symbols plugged in. So that equals to, once we did that, and then which equals to that, and that, and that, and simplified, and so on. And at this point, we're going to divide everything by x squared. Or, yeah, that way the numerator has only -7 left. And the denominator will become whatever. Arrange that, and it end up being -7/3. And that's problem 16. And I also plotted this out to confirm that this answer is correct. Okay, here's the function. All right, the red line, and then the blue line is the answer, -7/3. X is going to infinity, and as you notice, it converts to the limit very, very quickly. See, and it hasn't even gotten to what, 5 yet, and it already slapped right onto it. So that looks very, very nice. See how beautiful that is? And you should really plot this yourself too, because Desmos is such a nice program. So next, let's look at problem 17, which now this time we don't have a limit to do, but this is just a matter of testing your how good you are at doing differentiation, actually. So the limit of this thing is equal and what? Okay, let's see, f minus, we're calculating the limit of this thing, right? And there are a lot of symbols here. There's f and g and h and all that stuff. But just think carefully. Okay, what is that? That is just a function of x. So let's let big F, okay, f x, one variable, equals to f of g xx and h xx. So then this equation is the same as the limit of f of x minus f of a, and then divided by x minus a. That's all this thing is, which by definition of differentiation, that equals f prime of a, right? And next, if f of x is this equation, then what is f prime of x? F prime of x effectively would be f1 times g1 and g2, right? They both have x in it, and plus f2, same thing, times h1 and plus h2 by the chain rule. And so that is the answer. And we're gonna, so what is f? And then but the original limit is f prime of a, so we'll plug a in here in this f prime of x, and which gives us all this. Okay, so we write a many times, but that is the answer. It's just this thing with a plugged in, all positions of x. And let's see, yeah, so then it's this stuff added up, except you have to write down all the a's. So that should be right. So next, let's look at problem 18. To do problem 18, you have to first know what is the directional derivative, okay, which we did many months ago, and now it might be hard to remember. It is on page 40. The directional derivative, partial f partial psi alpha is f1, okay, times cosine alpha. Cosine alpha is a constant in this theorem, and that is the direction of which way psi is pointing. So it's just a constant, and then f2 plus times sine alpha. Now at this point you might think, well, it's been a while. I look at this, I don't quite remember what it's about. That is of no consequence. Just remember this is the formula, and we're going to use it. Okay, you don't need to know what it means exactly. You can still use it. At least to do this homework problem, and that's all we care about right now. So knowing this, let's tackle the homework. Knowing this is enough for you to do the homework, okay, without knowing the details of what it means. So then by the theorem 9, page 40, the partial f partial psi is equal to this thing right here that I just copied down, where alpha is some angle, constant angle, okay? And then I'll also call this thing gxy. For convenience. So let's define big F of x is partial f partial psi of x cosine alpha, x sine alpha. Now look at this very carefully, okay? Partial f partial psi already has various cosine sine there, but we'll ignore it and plug the x cosine alpha right into where x is, because this is the definition of this function. So this then will be, when you plug everything in, will look like this, right? F1 with, instead of xy, you'll have x cosine alpha, x sine alpha in it. So that's big Fx. If that is the case, then the original, the limit of this thing right here, which is our problem, right? Let me look at the problem again. This is problem 18. Where is it? Yeah, here's the original problem where we have the limit of partial this thing over partial psi alpha, and then at 0, etc. That and divided by x over here. Okay, that is the same as if we write that out. That is the same, which is this limit right here. That's the same as the limit as x goes to 0 of big F x minus big F 0. Okay, divided by x minus 0. In other words, this is equal to f prime, big F prime of 0. Now, therefore, what is big F prime of 0? We can first calculate what is big F prime of x. That will be equal to, we'll slap on the chain rule again. This is somewhat similar to problem 17. So big F prime of x, it will be cosine alpha and then f11 times cosine alpha. So please do that, okay, doing this part. And bearing in mind that big Fx equals to this thing. So when you take the derivative, then with respect to x, okay, so then you calculate each one, f11, f12, and then f1, f21, and f22. And now that we know that, and that is the answer, because we will calculate big F prime as 0 would be the answer. That is, which I have written down here. So the answer with the limit we are calculating is big F prime of 0, and that would be equal to all the functions evaluated as 0. Okay, with the alphas tagging along. That's about it. However, if you look at the back of the book, that is not the answer they gave. They gave the answer in a different form. They said the answer equals to this thing right here, which is fine. That just means we need to calculate this thing. Now, what is this? Okay, the second derivative. Now, to calculate the second derivative, we pretend that the partial f partial psi alpha, we'll call it gxy. Okay, and then we'll use gxy and plug it in, calculate what is partial g partial psi alpha, because partial g partial psi alpha is the same as the second derivative, right? And that's what we're shooting for. So being that g is the first derivative, if you take partial g partial psi alpha again, that would be the second derivative, and then plug this whole thing into the original formula, which is this thing. Okay, so how to do that with bearing that in mind and plugging things in, then we'll have this pile of stuff, please do this yourself, okay? We did this and this is slightly confusing, but if you think carefully, it would all come out. That is, we'll have the F11, F12, and F21 and F22 out. So because you're using this, plugging this thing, applying this partial differential, this formula onto this thing itself. That is, you have to, well, you're doing the second derivative, so you're doing the same process again. So please make this come out, okay? And this is how partial g of partial psi alpha by plugging it in. So then it will be F11 and F12 and all those things. Yeah, specifically I have it marked here, okay? E equals cosine alpha times G1. So you calculate what G1 is, and then similarly sine alpha times G2, you calculate what G2 is, and then this will come out fine. And as a result, you notice that this is exactly the same as f prime of 0. So f prime of 0 equals this thing, and that is the answer. So that concludes it. And this is just a matter of testing our ability to do partial differentiation in chapter 1 again. Next, let's look at problem 19, which I think it worked out pretty good, although it looks a bit hard. Okay, you have log there, but it didn't turn out to be so bad because first we confirmed that this is 0 times negative infinity as x is approaching 1 from the negative side, and so we turn it into the infinity over infinity situation, took the derivative which equals to this, and then then now is a 0 over 0 situation. Simplify it slightly, okay, to become that, and then realize that this thing is and then take derivative again. So we got here. So at this point, then we're able to calculate it. There's the bottom then, since x is going to 1, log x is 0, so the denominator is no longer 0. So we can evaluate this thing, and it turns out to be 0. So the expression, the function, the original function then approaches 0, which I don't think this one has the answer at the back of the book. And so, as always, we plot it into the Desmos calculator, and you notice the function, okay? But it does go to 0 from the negatives from left side of 1. See, as x approach 1 from the left side, it goes to 0. And I think any further is not defined because of the square root situation here. So that is look at how awesome it looks. You just Desmos plotted it perfectly smoothly, which I totally appreciate. So that's problem 19. So next, let's look at problem 20. I don't think there's any tricks in problem 20. It is a 0 times infinity situation, which we turn into an infinity over infinity situation, take the derivative, which quickly got up to be 0 over infinity situation, which the answer is 0. And I also confirm that by looking at the calculator, which does confirm what I said. See, as x goes to 0, then the function does approach 0 at 0, 0. So that looks pretty decent. Right? That's problem 20. And in fact, it approached 0 rather quickly. It just took a dive. And anyway, that's that. And then next, we will consider problem 21. So next, let's consider problem 21. We have the limit of this thing that looks pretty complicated, right? So let's consider the first part. The first part is a 0 plus 0 times infinity situation. And if we rewrite it, we'll just write down the inside as y, okay? As x goes to 0, y goes to infinity, same thing. And then which if we take the derivative, it ends up being 0. So it goes to 0. So the first part goes to 0. The second part, if we look at it more closely, as x goes to 0, it just equals to 0. So it's 0 times 0 equals to 0, and that's the answer of problem 21, which I plotted out here, and thus confirm my calculations. Let's see, problem 21, and the graph as x goes to 0 from the positive side, it does go to 0. Okay, so that's problem 21. Okay, next let's do problem 22. We have another integral situation. I should mention that in this problem, it's not necessarily obvious that the integral even is it goes anywhere. Like, does it? We need to, before we apply L'Hopital's rule, that is by taking the derivative, we have to first prove the integral goes somewhere. Okay, what as x go to 0. Where does this thing go, really? I mean, it might go to infinity, it might go to 0. We need to know that first. So to know that, let's examine the integrand, the function inside. Okay, this thing, which is that, and then we do some calculations and realize that as t go to 0, this thing actually converges to a value. It converges into a 2, which means the integration, if you integrate from 0 to x as x go to 0, does go to 0 because you're integrating a finite number. So a finite function. So this becomes a 0 over 0 situation here, right? So this integral does go to 0, and so this becomes a 0 over 0 integration if you consider x the denominator. So now we can apply the L'Hopital's rule and the fundamental theorem, and which means take the derivative. It becomes that thing right here, right? And divided by just 1 as applying x go to 0, and that is equal to let's see, as x go to 0, then let me think. Yeah, as x equal to 0, that equals to something. And let's see, where is it? This thing equals to e squared. How do we know this? It's because we already did this. That is 1 plus t, 1 over t is putting it in here. Okay, the part in here equals to 2. So the whole thing then converges into e squared. So we already did this. So we know this thing as x goes to 0 equal to e squared, as we have just done. So the answer is to problem 22 is e squared. The important part of this problem is that you have to, instead of just jump ahead and apply the L'Hopital's rule, you have to confirm that this is indeed a 0 over 0 situation before you're allowed to apply the rule. So problem 22, I think I also have a graph here. Okay, the thing is, well, the graph just shows that it converges at e squared. Okay, there's a fairly complicated looking thing. Is that problem 22? Oh, I didn't plot. Oh, okay, never mind. So I plotted this part of the problem where the function goes to e squared at 0, and also the actual problem we're doing. Okay, this thing then converges at this thing as x approaches 0 equals it also at e squared. Okay, y equal to e squared, and so that is our answer. And that is, yeah, look at how nice it looks, okay? And Desmos, remember, Desmos is able to plot functions with the integral sign inside. You just type in int, the letters int, and then the integral sign will show up, allowing you to type in the rest of the stuff, including the limits. So that is, look how beautiful it is. I'm very, very proud of it, okay? So that is problem 22. So the next problem, we do problem 23, is we're supposed to find out what's wrong with the solution that's presented. There's a fallacy in here. Well, the fallacy turns out to be very direct. The very first sentence is wrong. Okay, this does not equal to that because this only works if the denominator is not going to 0. Okay, the limit division rule, as I copy this down from AI, says that this equal to that, sure, assuming the denominator is not 0. If the denominator is 0, then the whole thing falls apart into a mess, and you don't know what you're getting. So then, and then later in the proof, then it made the same mistake, and that from going from here to here, again, the denominator is 0, so you can't write that equation sign there. Okay, that is that part is also wrong, but otherwise the proof is okay. But being that it has two mistakes, and the answer turns out to be wrong. Now the book doesn't really ask us to figure out what the right answer is, but let's do that anyway. Okay, how do you calculate the limit of this thing? All right, so here's what I did. To calculate this thing, it is a 0 over 0 situation. So I took the derivative, which got me here. And then I rearranged this somewhat. And then give me a second here. Actually, I think I rewrote it on the new page. So here's the original function, which is a 0 over 0. So we took the derivative, got here, rewrote it a little bit, and then took the derivative. Is this also rewriting? Yeah, I think so. This is just a rewriting, okay? And then took this is still 0 over 0, so took the derivative again, got here after making some mess, got here, and by now you notice that we're not really doing any better much. So the x's can be canceled here, but what we're gonna do at this point is we're gonna divide everything by something. What are we dividing by? X. Okay, so divide top and bottom by x, and that's not counting the x's that canceled. So then what we have is sine x over x on top, and then some sine x over x on the bottom, and there's an extra x here, so that get divided out. So we got this. And remember, sine x over x equal to 1 because x is approaching 0 here. So then that becomes a minus 1/2, and then there's a 1 on top, a 2 on the bottom, and 1. So altogether it becomes negative 1/6. And that is what the function is going to. And the book said calculated in the wrong way to be minus 1/2, which is wrong. Okay, the actual answer is negative 1/6. And as always, I plotted it into the calculator. So see, I plotted it into the calculator right here. And as you can see, the green line is the function. Yes, and then the blue line is where it's going. As x approaches is the answer, minus 1/6. And as you can see, as x approaches 0, everything does approach minus 1/6 like it's supposed to. So my answer is confirmed to be correct. And so that is that. And I also want you to pay attention to the sine x over x, which is part of this problem. Okay, we used it to solve this problem. And because sine x over x goes to 1 as x approaches 0. And that's true no matter which direction x approaches. See, and because sine x over x appears to be an even function. How interesting. Anyway, the reason I show it to you here, because sine x over x looks very good, doesn't it? It looks there like the water waves gently rippling. And also, I don't think I have ever really plotted it before. Okay, we've used sine x over x a lot, but we've never plotted it, I don't think, to see what it actually looks like. Well, here's what it looks like. And of course, it goes to infinity. The rippling water quickly flattens in the end, but it has a nice smooth ripple in the middle, and I think that looks very nice. So I just want to show you this so you have a idea of what sine x over x look like. Not that it necessarily will be useful, but hey, it looks good, and that's all that matters. So that should conclude the end of this section.